This
All right.
conference will now
So
be
to start
recorded.
with, in the previous class, you must have discussed about the UART protocol. So that is Universal Asynchronous Receiver and Transmitter. So you have got a fair idea of which and all protocols we are going to discuss throughout the module. And initially, the very first protocol, that is UART, has been done. And if I'm not wrong, you know how to configure the UART right now, how to make use of the QtCom if you are in the Windows, and how to make use of the Minicom if you're in the Linux operating system, and also have to make use of the Terraterm. So instead of QtCom, because it has got some small bug in it, so we can still go with the Terraterm also. And I'm hoping all of you are able to make use of that. So UART was by Intel, and today we are going to start with the SPI protocol. So the one which you discussed in the previous class, the UART, was a interboard protocol. So you used to communicate with between two different boards. So for example, in our case, what we did was whatever you used to type on the serial terminal has to reach to the microcontroller, and that was transmitted back to your serial terminal. So this serial terminal is been installed in one board, that is your what say your motherboard. So the processor, the whatever is there. So that is one IC, and you were communicating with the microcontroller. So on the Pixing Lab board, so we have got our PIC microcontroller, and communication was happening between two different boards. So the next protocol we are going to discuss, that is SPI, is an intra-board protocol. So in this case, two chips are communicating, which is being placed on the same board. So here the SPI protocol, which stands for Serial Peripheral Interface, is a protocol, and this was by the company Motorola. So what actually happened is, in this protocol, the one which has been designed by the Motorola, so is for the communication between the two ICs on the same board. So we are going to study the introduction of this protocol first, and then we are going to understand the interface, that is the kind of the hardware configuration, and also we will see the data transmission, which I also can consider it as data validity, that is when is the data being written and when is the data being read. So we will discuss these things with respect to the serial peripheral interface, that is the SPI protocol. So let us start with the very first thing here, which is nothing but the introduction. So let us discuss few things with respect to the introduction of SPI protocol. Now, as I said, this SPI is a serial peripheral interface, and it has got these three main features. So first one is, it is a synchronous protocol. Okay, now the very first thing I'm saying is it is a synchronous protocol. Now, may I know, if it is a synchronous protocol, communication is happening with respect to what? What is present if it is a synchronous communication? Because what you discussed was an asynchronous. So this is a synchronous protocol. What will be definitely present for you, and how is the communication happening? Yes, remember, there is a clock line present, and communication is happening with respect to the clock. So always there is a master, and the master is going to generate the clock, and with respect to that clock line, the data transmission happens. So that is the first feature of SPI protocol. This is a synchronous protocol, and communication is happening with respect to the clock. And another feature of SPI is it is full duplex. So this protocol is full duplex. Now tell me, due to the full duplexity, how many lines will this protocol should definitely have? How many lines the protocol should definitely have? If the two ICs have to communicate with each other, and this protocol offers me full duplex, how many lines, how many data lines do you think is definitely necessary? Come on, how many data lines do you think is definitely necessary? First of all, what is full duplex? Can you people tell me what is full duplex? Guys, unless and until you are not Responding, it is difficult for me. Yes, both can operate at the same time. So two-way communication, right? So the full duplex means it's two-way communication where both the parties can communicate at the same time. So one can transmit at the same time the other can be receiving. Yes. So because of the feature of full duplexity, there has to be definitely two data lines for the sake of transmission. So one for the transmission, the other for the reception. So if two parties have to communicate at the same time, there has to be definitely two lines present, and this is about the full duplex. So we just got to know this is synchronous. So one line is the clock line. This is full duplex. So we will have two data lines. And now the systems which is being communicated can be addressed as master and a slave. So here we can use the terminology as master and the slave. So what happens is one line is the clock line, the other two are the data line, and I can refer the devices as master and slave. So previously in UART we used to refer the device as host and the device. So we didn't have an option of calling it as master and slave, but we do can address the devices as master and slave in case of SPI protocol. Okay, so we can refer it as master and the slave. And remember, this SPI protocol is it is a single master multiple slave protocol. Okay, so I am writing it here. So it is single master multiple slave protocol. So here there is a single master which can communicate with multiple slaves. Now I just said there is a single master who can communicate with multiple lines. Do you think there is a need of any other line apart from the two data lines and one clock line? What do you think? Do you think there is a need of another line apart from these three lines? Come on, I'm saying the master can communicate with multiple slaves. So if a master can communicate with multiple slaves, don't you think there has to be a line where a master can select a particular slave? So there are multiple slaves and a master can communicate with a particular slave by using the slave select line. So there is another line present apart from the clock line and the two data lines. There is another line present which is called as the slave select line, and that slave select line is the one which helps the master to pick the slave with which it wants to communicate. So because it is multiple slaves, what a master can communicate, there comes an other line called as the slave select line. So that is about the SPI protocol. Now if you see, as per our discussions, let me go with the next slide. So you can see, as per our discussions, the protocol is going to have four lines for sure. So one is the serial clock line, which is given the name as SCLK. Then the other two are the data lines. MOSI and MISO are the data lines, and ENSS is the slave select line. So MOSI here stands for master out, slave in. MISO here stands for master in, slave out. And NSS is the select line, the slave select line for multiple number of slaves present in the given communication protocol. So whatever names you see here, please remember these names, and these names are given by the SPI standard. The Serial Peripheral Interface Protocol standard has given the names as SCLK, MOSI, MISO and ANSS, and you have to go with the same names. Different companies give different names. For example, if there is any protocol being designed by National Institute, they say this MOSI, MISO as data in and data out. So it all depends on the company which have the manufacturer which are given the name. So Motorola, who designed the SPI protocol, has fixed these standard names. So serial clock line, master out, slave in, master in, slave out, and the slave select line. Okay. Now, as I said, this is a master, sorry, there is a master. A master can communicate with the slave. So I said there is a clock line present, and there is MOSI MISO present, and also a slave select line. Let us see an example. So here you can see an example. This is a single master, single slave example. So here there is a single master who is going to communicate with the single slave. Now, if there is a single master and single slave, you just observe the names. So observe the direction of the lines. NSS means slave select line. SS is the slave select. N stands for the numbering. So first slave select line, second slave select line, third slave select line, depending on the number of slaves present in the network. Okay. So this is an example where a single master is communicating with a single slave. So please see how the how the direction of the line is and how the communication is happening. So first of all is the slave select line. First of all, the very first line you see is the clock line. And remember, the clock is always being generated by the master. So master generates the clock all the time. That is why you can see a line going from the master to the slave. So see the direction of the line. It is from the master towards the slave. Always remember, master is the one who's going to generate the clock. And next, so if you see the MOSI stands for master out, slave in. Means master is giving out the data, slave is receiving it. So that is why see this red line and its direction. So it is towards slave 1 because master is transmitting this time, and all the data from the master is going to the slave, and slave is going to receive that. Hence the direction is towards the slave. And next is master in, slave out. At this time, slave is giving the data and master is receiving it. So observe this green line and its direction towards the master because slave is transmitting this time and master is receiving. So this is MISO. And then this is the slave select line. So it is SS1 because there is only one slave. You either can call it as 1SS or SS1, whichever you are comfortable with. So SS1 is the slave select line for this first slave. So because this master is going to communicate with slave 1, so the direction is like this. Okay, so there is a slave select line. Master is going to select the particular slave, hence the direction is like this. And these are the four lines of the SPI protocol. So any communication is happening using SPI protocol should definitely have these four lines. Okay, but what did I say? This protocol is capable of doing single master multiple slave communication. So I didn't say there is only one master, one slave. So this communication protocol is capable of communicating with multiple slaves. So there is only single master. I'm sorry. So there is only single master who is going to communicate with multiple slaves. So tomorrow you might have the chances of going with multiple slaves, and you have to be selecting the particular slave device for the communication. So master can be just a microcontroller who's going to have the clock line generated. So let's say master is the microcontroller, and who can be the slave? There are multiple devices who can be a slave. For example, it can be an RTC, it can be a temperature sensor, EEPROM chips, it can be DAX, it can be some flash memory. So all of these are the examples of slaves. So there are many devices who can act as a slave, and if you see the interface, this is how the interface will be actually present. And if you can notice this, can you tell me how many slaves do we have in this configuration? How many slaves do we have in this configuration? Yes. So we actually have got 3 slaves. This is a single master multiple slave example. So there is a single master, if you can notice, and the slaves are, we have got 3 slaves. So that is why, if you can see, master is going to generate the clock line. Hence, if you can notice, there is only one clock line which has been commonly shared by all the slaves. So you see here, master is going to generate the clock line that has been commonly shared by slave 1, slave 2 and slave 3. And then if you can see the MOSI, it is master out slave in. So see, it is going to communicate with multiple slaves. So the common connection of MOSI of master is going to MOSI of slave 1, also to slave 2, also to slave 3. And similarly the MISO. So whenever the slave has to transmit and master has to receive, it has to make use of this line. And apart from that, because I have got three slaves, there are three slave select lines. So there is SS1, there is SS2, SS3. Okay, so because there are three slaves in this network, there are three slave select lines. Now, let's say I want to select a particular slave. Okay, so just an example, I want to select a particular slave. Example is, let's say master wants to communicate with slave 2. Okay, so master wants to communicate with slave 2. And how is the communication happening? With the help of this SS2. Okay, with the help of this SS2, it is going to select the particular slave. So using SS2, it is going to select slave 2. Now, point to point communication happens between the master and slave 2. Okay, with the help of SS2, it selects the slave 2, and when slave 2 is being selected, communication is happening between the master and the slave 2. And guys, remember, there's no communication happening with slave 1 or slave 3. There is only communication happening between the master and the slave 2. So whatever data is being transmitted by the master, it is going to the slave 2, and whatever slave 2 is being transmitted, it is going to the master directly. So basically, using the slave select lines, you can select the particular slave and you can do the point to point communication directly. So from the master to the specific slave, there can be point to point communication happening. Tomorrow, if I want to communicate with slave 1, the only thing I do is make use of this SS1. So with the help of this SS1, I'm going to select slave 1. Now the communication is definitely happening only between the master and slave 1, and there is no communication happening with slave 2 or slave 3. So like this, again, if I want to communicate with slave 3, I'm going to make use of SS3. I'm going to make sure the point to point communication is happening only between master and slave 3, and the slave 1 and slave 2 are not being involved. Okay, so this is how a single master is going to communicate with multiple slaves. So guys, remember, it is with the help of the slave select lines. Okay, now if you look into this configuration, okay, if you just look into this configuration, do you see any potential issue in this? If you look into this configuration, any potential issues means some issue which might occur going ahead. So later days, do you see any potential issue happening with respect to this configuration? Come on, do you see any issues happening? You can give me an example. So if yes, please say yes. If no, please say no. Number of slaves complexity, yes. Do you people agree with what Sandeep says? So don't you think tomorrow, let's say if I have got 10 slaves, how many slave select lines should I be going with? If there are 10 slaves uh, in the configuration, how many slave select lines do I require? Come on. So if you people are this least responsive, it is literally difficult for me to go ahead. Yes. So if it is 10 slaves we are going with, I have to go with 10 slave select lines. For example, if there are 100 slaves in the network, I might require 100 slave select lines. So remember, going ahead, there can be a hardware complexity. So the number of wires increases, the number of hardware complexity is going to increase. So this is an issue from the hardware side. As the number of slaves are increasing, the number of wires are also increasing. So this is an issue with respect to this configuration of a single master multiple slave. Now, due to this disadvantage of single master multiple slave, guys, remember there is an other configuration, and the other configuration is nothing but the daisy chain configuration. So if you can notice, this is again the same type. A single master is used to communicate with multiple slaves, but the configuration here, if you can see, is the daisy chain configuration. So why is it a daisy chain? I hope you people have seen a daisy chain thing. So how the flowers are being cascaded, how they are being connected one to the other. So similar to that, we have a daisy chain configuration. Now, if you can notice, in case of slaves, okay, highly, you please observe in case of slaves. So here there is one master. As I said, anyways, this protocol is going to support a single master, multiple slave. So there is only one master, and that master is like a owner who's going to generate the clock cycles. So master generates the clock, and hence it is a common line. And MOSI of slave 1, if you can notice, is connected to MOSI of the master is being connected to MOSI of slave 1. Okay, then if you can notice, MOSI is going to get connected to slave 1, but what about MISO? So MISO of slave 1 is being connected to MOSI of slave 2. MISO of slave 2 is being connected to MOSI of slave 3, and then MISO of slave 3 is being connected back to the master. So don't you think between the master and the slaves there is a cascade connection? Yes or no? Don't you think there's a cascade connection? Master has been connected to the slave 1 to slave 2, slave 2 to slave 3, and the last slave is being connected back to the master. So these slaves have been connected in a daisy chain connection. So please observe that. And how many slave select lines can you observe in this configuration? In the daisy chain configuration, how many slave select lines have been there? Come on, how many slave select lines have been there here? There is only one slave select line. It doesn't matter how many slaves have been there in this network. So how much ever slaves it might be, there is only one slave select line. Okay, so whatever issue was there in the previous configuration, that issue has been resolved here. So previously the number of slaves increases, the number of slave select lines were also increasing, and the wires were increasing. In turn, hardware configuration was a little difficult. But coming to this is a daisy chain configuration. There is only one slave select line using which you can select either of the slaves. Now, what does this indicate? This indicates that there is only one slave select line and it has been common among all. Now, I cannot specifically select a line. So that is another disadvantage here. Okay, so remember, I cannot specifically select a line. When data transmission is happening, whatever data is there in master, first it comes to slave 1, then from slave 1 to slave 2, then slave 2 to slave 3, and then from slave 3 back to the master. So let's say master wants to communicate with slave 2, he's going to select that slave 2. But the thing right now is, if he wants to transmit some data to slave 2, it first have to transmit it to slave 1. Slave 1 then transmits it to slave 2. So it is quite challenging at times. Or let's say slave 1 want to give the data to the master. So slave 1 has to give it to slave 2, slave 2 will give it to slave 3, later slave 3 is going to give it to the master. So that is one disadvantage. Advantage is the number of hardware lines, hardware wires are going to be reduced. The disadvantage is there is no point to point communication happening here. Okay, you cannot select a specific slave and do the configuration. Whenever I have to transmit the data, it is not happening directly from point to point. It is with the help of other slaves as well. So that is about the daisy chain configuration. So all the configuration has got its own advantage, has got its own disadvantage, and we have to be picking the configuration whichever suits the best according to the requirement. Okay, now before I go with the next thing, that is the working principle of this SPI protocol, is it clear up to this much? Are you people clear with the normal configuration where a master is communicating with 3 slaves and daisy chain configuration where a master is communicating with 3 slaves? Okay, fine. So now, let's say there is a single master single slave configuration. What happens here is master and the slave are getting connected. Okay, so master and the slave have been connected in this fashion, and remember, this is a kind of a circular shift. So there is master, there is slave, master and slave have been communicated in this manner. So now I want to do the communication between the two. There's a master, there's a slave, they want to communicate with each other. And this is how the communication happens. And if you can see this, it looks like a circular buffer. Okay, so if you take the internal of this master and the slave, you can see the path, or you can directly look into the pattern. And as I said, if you see the internal of this, every device will have a connection done like this. And guys, remember, every device, as you have discussed in UART, every device is going to have a shift register. Okay, so in UART also, you couldn't write the data directly. So it is not something you can write directly or read directly. So there are presence of shift registers using which you are going to do the operation. Either it can be transmitting or it can be receiving. Things happens with respect to the shift register. And here also there is a presence of shift register. Okay. Um, I hope you know what a shift register is. In that case, if it is a shift register, data just gets shifted. Okay. So here also, if you can notice, these are the shift registers. Let me highlight it. So this, if you can see, is a shift register. This is also a shift register. And if you can notice, the connection is like a circular buffer. Okay, so you can see the last bit, this bit is going to sit at this particular position, and this bit is going to sit at this particular position. So this is acting like a circular shift. Anything what gets transmitted out of this meso, so comes to the slave, the MSB of the master comes to this LSB of the slave. Similarly, MSB of the slave comes to the LSB of the master. So they have been connected in a circular manner, and data gets shifted on a circular manner. Okay, so connection is happening in a circular manner, hence I can generally call it as a circular buffer. And what happens is, anything I push out of the master is going to get its place at the slave. Okay, so physically there is an interconnection happening. So anything I push out of the slave is going to find its place in the master. Anything I push out of the master is going to find its place at the slave. Okay, for example, let's say, okay, so let's say, for example, there is this one which you want to transmit. So okay, I think I have already shifted. Okay. So initially this is what I have. Master has got 10100011 and slave has got 00111010. So let's say I want to shift this. Okay. So this one finds its place at this particular position. You see? So whatever one was here, it took its position here, and whatever was in the MSB got shifted to the LSB of the slave. Sorry, LSB of the master. Similarly, if I shift it for another time, this 0 is going to find its place at the LSB of the slave, and 0 in the MSB of the slave is going to find its place at the LSB of the master. So like this, shifting is going to happen. See, initially what did I have? Let's say in the hexadecimal format, this is 0x, 1010 is A, 0011 is 3, and here it is 3, and 1011 is, I guess, B. Not guess, that is B. So now let's say I'm going to shift it for the very first time. So this is how the shifting happens for the second time, for the third time, fourth, fifth, sixth, seventh, and eighth. Now if you can see 00111011 is it the master, and slave is having 10100011. So this is how you're going to literally exchange the data between the master and the slave. So with the help of the shift register. And now if I shift for another time, do you think the data is properly being received by the slave? So if I'm going to shift it for another time, do you think I'm going to receive the proper data? Do you think the proper data gets received? Come on, either it is Mosi or me, like whoever is been transmitting. So do you think the data is properly received if I shift it for another time after 8 times? So remember, no, you don't end up receiving the data. Will every time, sorry, let me read your doubt. Will every time slave only send the data to the master? So first of all, master is sending, if you can notice here. So I had to highlight that point. So this is master. Master wants to send the data. So it is up to the communication requirement. If master wants to send, master is going to send. If slave wants to send, slave is going to send. Okay, it is all up to the requirement. So in this case, actually master is transmitting and slave is receiving. Okay, so similarly slave is going to transmit, master is going to receive. You see here, master is going to transmit this one, which is going to sit at this particular position. And what is the slave doing at the same time? It received that. Also, it it shifted this bit which was at the MSB to the LSB of the master. Now, don't you think full duplex has been achieved? Two things are communicating simultaneously. Master is transmitting, slave is receiving. Also, slave is transmitting, master is receiving. Don't you think full duplex has been achieved here? So yes, it is not every time the master is going to transmit. It is all up to the communication. So if slave wants to receive, slave is going to receive it. If slave wants to transmit, slave can even transmit. But both transmission and reception, remember, is happening with respect to the clock pulse. So you should not forget that. So here what happens? Master is transmitting, slave is receiving. Simultaneously, slave is also transmitting, master is receiving. And this is how you are going to achieve full duplex. Okay. Now, as I said, the communication is happening between the master and the slave. I'm sorry. So communication is happening between the master and the slave. And I said the communication is going to happen with respect to the clock pulse. Okay. Now comes the question of how the clock pulse is getting generated. So remember, master is the one who's going to generate the clock pulse. Okay, so every time whoever has been transmitting, whoever has been receiving, so it should happen with respect to the clock pulse, and master is going to generate the clock pulse. Now you should know how is the clock pulse getting generated. So this clock pulse by the master can be generated in two ways. Okay, so first way is with the help of the built-in peripheral. If there is any SPI protocol block which has been present inside your microcontroller, it is going to generate the clock pulse for itself. And if the SPI protocols block is not being there in your microcontroller, if your microcontroller is not supporting SPI protocol and you still want to achieve the SPI protocol, then you have to externally generate a clock pulse. And how are you going to externally generate a clock pulse? I hope you know, by using the bit banging method, whichever we discussed previously. So using the bit banging method, you are going to generate the clock pulse, and with respect to that clock pulse, the communication is going to happen. And to achieve this shift, you might have to go with the for loop. So generate the clock pulse using bit banging method, and to achieve the shift operation, you will have to be going with a for loop. Shift the data bit by bit for 8 times. So that is how you are going to achieve the transmission of the data using the SPI protocol. If transmission or reception of data using SPI protocol, if there is no built-in block available. So you are going to generate the clock pulse using bit banging method, and you are going to transmit the data or receive the data using the shifting operation, which you are going to achieve by writing a for loop. And if the built-in peripheral is already present, let's say you have a microcontroller which supports SPI protocol and it has a built-in block for the SPI protocol. In that case, you remember there is just only one thing you will have to be writing. So let's say I want to transmit some data. Okay, so assume I want to transmit some data and I already have got a built-in peripheral of the SPI protocol. So the only thing I have to do is I have to transmit the data, and I hope you remember that you cannot write the data directly into the shift register. That is not possible. Writing the data directly into the shift register is not possible. So in that case, what we will do is we will go with the buffer register. Yes. So you should not forget you are going with the buffer register. So you just write something like this. For example, let's say I want to transmit some data like just a minute. So let's say I want to transmit some data like 0xAA. Okay, let's say I want to transmit this. So what I'm going to do is I'm going to go with the buffer register, write the data into the buffer register. So then the moment you write the data into the buffer register and this instruction gets executed, the built-in SPI block is going to generate 8 clock pulses, and then this data is being returned into the shift register, and using that shift register the data gets automatically shifted from the master to the slave or from the slave to the master. But the only thing you have to do here is wait until the shifting operation is done. Okay, so you write into the buffer register, then the data has been returned into the shift register, then the shift register shifts the data to the shift register of the corresponding slave. So the only thing you have to do is wait until the shift register has shifted all 8 bits of data. And how are you going to wait? You either can do it using the polling method or you can do it using the interrupt method. Okay, so there is some bit, okay, just as the top UART there will be a bit, and using that bit you can either go with the polling method or the interrupt method. So that is how a built-in SPI protocol block will work, and how if there is no SPI built-in protocol is going to be present. Understood? Now we are transmitting A3, but slave received 3B data is modified. You no, slave has not received B3, sorry, 3B. So first of all, I want to transmit A3. Okay, this is some data which is already present in the slave. So this is an electronic device. It is a register. Some data must have already been there. I just want to make sure this A3 is going to the slave. Okay, that is the only task. Whatever I want to transmit, I want to transmit it to the slave right now. So I'm going to write, for example, if there is if there is any built-in SPI block, I'm going to write it into the buffer register. That buffer register is going to write A3 into the shift register, and data will be shifted bit by bit with the help of every clock pulse, and at the end slave is going to receive that A3. That is what I mean. Okay. Similarly, if slave want to transmit the data, so slave is going to transmit with the help of the clock pulse. And how is the transmission happening? From the shift register of slave, data is coming to the shift register of the master. Okay, what gets at the slave is of least bothered. So whoever is transmitting, the aim is just to transmit. What he gets is least bothered because he is not required. So at the same time, 3B gets shifted to the master as well, but master doesn't need that 3B. So he can just ignore it. Okay, something has to come fit back to the place, so he can just ignore it. He doesn't want 3B back, he can just ignore it. Later, if master wants to write another data, so again the data will be written here. It is made sure it is reaching the slave. So what slave is giving is least bothered. Okay. Similarly, let's say slave want to transmit the data. Slave makes sure the data is being reached till the master, and whatever slave is getting back is least bothered. So the connection is like a circular shift for sure, but when it is transmitting, whatever it is receiving is least bothered. Okay, I hope you people got this. Everybody, is this been clear? Okay. So this is how the SPI protocol has been working. You either can make use of the built-in SPI block, or you can have your own SPI protocol implemented. As I said, first there has to be a clock pulse generated. You can go with bit banging method, and then you have to make sure that the communication is happening between the two devices with with the help of the clock pulse, and the transmission and reception is happening accordingly. And if there is SPI protocol built-in block already available, your work is very simple. You just enable the protocol. You just have to, whenever you want to transmit the data, write it into the buffer register. The data gets transmitted accordingly. The only thing you have to make sure is wait until the data has been transmitted. And you can do it with the help of a bit using either polling method or the interrupt method. So that is how SPI protocol is going to work. And also I hope you got how full duplex has been achieved in this case. Now, if you can notice, I said MOSI, MISO, SC, LK are the names which have been given by Motorola, and you have to stick to the same names. But can you observe there is SDI, SDO, SCK and CS? So can you observe this in the slave? Okay, so now let me tell you what is this SDI, SD0, slave and the SCK and the CS. So first of all, SDI, these are the names, whatever you are seeing here, these four are the names which are being given by the manufacturer, the slave manufacturer. So he is going to tell, I am a slave manufacturer, I am going to manufacture a slave, and I am definitely sure that this will never going to be a master. Okay, so it's telling that this slave, whatever I have designed, is never going to turn out as a master. So why to call it as master out, slave in, or slave in, master in, slave out and all? Because this is never going to act as a master. So that is why a slave manufacturer gives the name as SDI, SDO, SCK and the CS. So SDI stands for slave data in, SDO stands for slave data out, SCK stands for serial clock, and CS stands for chip select. So different company might give the different name. Concept wise, the things are same. but the names wise it depends on the manufacturer, whoever is manufacturing the device. So that is how the protocol is actually working, and I hope this much of the things have been clear. Now if you can notice, okay, let's go with the next thing. If you can notice, I said that you are going to transmit the data, you're going to receive the data, and I also said this is going to be with the full duplex manner. So full duplex protocol is the thing here, and also there is a presence of clock line because this is a synchronous protocol. Now data is being transmitted, data is being received. First thing, if it is transmission, means data is being written. Okay, so transmission means data is being written. Reception or receiving means data is being read. Okay, now question is, you have got a single clock line, and with respect to the single clock line, when will the transmission happen and when will the reception happen? Okay, remember, clock line will have two levels. Okay, either it is the low level or the high level. Also, it can be with respect to the edges also. So, falling edge or the rising edge. So remember, at the same level, there will not be any communication. Means both of the things will not happen at the same level. Okay, so one level is dedicated for transmission, the other level is dedicated for reception. Okay, so here this SPI protocol is an edge triggered protocol. Okay, this SPI protocol is an edge triggered protocol. So remember, whenever the clock line is falling from high to low, okay, so whenever the clock line is falling from high to low, all of the device, whoever wants to write, okay, the device whoever wants to write is going to write at this moment. When the clock line is falling from low to high to low, there is the data being written, all the devices are going to write the data. And whenever there is a transition from low to high in the clock line, all the devices are going to read the data. Okay, so all the devices are going to read the data whenever the clock line is going from low to high, and all the devices are going to write the data whenever clock line is from high to low. So there can be a question asked about the data validity of this SPI protocol. This is what data validity is. So you have to tell when is the write happening, when is the read happening. So write is going to happen whenever a clock line is falling from high to low, and means the data will be written in that case. And whenever there is a transition from low to high in the clock line, all the devices are going to read the data. And this is about the data validity of the SPI protocol. There is only one clock line, and with the help of the same clock line, both transmission and reception has to happen. So as you know, there is edge triggering, there is level triggering. So level in the sense you have got two levels, low level and high level. Edge trigger, you have got two edges, transition from high to low and transition from low to high. So this SPI protocol is edge triggered. Whenever the clock transmission happens from high to low, all the devices are going to write, means they are going to transmit. And whenever there is a transition from low to high, all the devices are going to read, that means there is a reception happening. And this is about the data validity. Clear? Okay, now let me go back to the two configurations. So I showed one normal configuration and the other was the daisy chain configuration. So let us understand this configurations, the two configurations. So this is the normal configuration, this is the daisy chain configuration. Now can you tell me, when will you pick this normal configuration and when are you going to, uh, sorry, Yeah, this is the normal configuration and this is the daisy chain configuration. So now my question is, when are you going to go with the normal configuration and when are you going to go with the daisy chain configuration? So one thing we have already discussed, if there is if there is multiple slaves present, so there are more number of slave present, there will be more number of hardware lines. Okay, so when peripherals are less, correct. So when more number of slaves are there, so you might want multiple slave select lines, the hardware complexity is going to increase. So in order to avoid the hardware complexity, you might have to be going with the daisy chain configuration. So that is one disadvantage of the normal configuration. Can I get any other reason of or any other scenario where you are going with a normal configuration and where you are going to go with the daisy chain configuration? Normal is more reliable. Depends. You cannot say this is not uh, reliable. Okay, so let me go with one scenario. Okay, so I'm going with a small scenario. So let's say in both the cases I'm using the same master. Okay, just remember both the cases the master is been the same. So slaves also, let's take the same. First is the normal configuration, second one is the daisy chain configuration. Now master is going to generate the clock pulse. Okay, let's say master generates a clock pulse like this, and for to generate every clock pulse, let's say master is taking 1 microseconds. Okay, so master is taking 1 microsecond for generating every clock pulse. Now to transmit 8 bits of data, how many clock pulses do I need? To transmit 8 bits of data, how many clock pulses do I need? Come on, to transmit 8 bits of data, how many uh, clock pulses do I need? 8 clock pulses, isn't it? So I want to transmit. See, I want to transmit, and transmission happens only when there is a transition from a higher level to the lower level. So that is at the falling edge. So every bit gets transmitted. So here to generate one clock pulse, the master is taking 1 microsecond. So to transmit 8 bits, okay. So if I want to transmit 8 bits, I want 8 clock pulses. Okay. So now let's say I want to transmit 8 bits of data to slave 1. Okay, assume I want to transmit 8 bits of data to slave 1. How much duration will I be taking? Correct. So I am going to go with 8 microseconds. So I am going to select slave 1 using SS1, and to transmit 8 bits of data from master to slave, I'm going to make use of 8 clock pulses, and in just 8 microseconds, I'll make sure the data from the master has reached to slave 1. What about slave 2? If there is master in this configuration, in this normal configuration, there's a master who wants to transmit 8 bits of data to slave 2 this time. So how much duration do you think it takes for transmission of the data from master to slave 2? Come on, I want to transmit the same 8 bits of data, and this time I want to transmit it to slave 2. How much duration do you think it will take? Again, it is just 8 microseconds, isn't it? So same. So the master is going to select this slave using SS2. So the moment it has to transmit the data, it generates 8 clock pulses. With every clock pulse, 1 bit gets transmitted. So to make sure the master is transmitting 8 bits of data to slave 2, it is again taking 8 microseconds. Then coming to slave 3. If master wants to transmit the data to slave 3, how much duration is it taking? Again, I'm going with 8 bits itself. Master wants to transmit 8 bits of data to slave 3. So how much duration is going it is going to take to make sure the data has reached slave 3? Don't you think it is same 8 microseconds only? So what is the conclusion here? First of all, point to point communication is happening. And remember, any number of slaves you take, it is going to take the same amount of time to reach certain data. So you take 100 slaves also. To make sure the master wants to transmit 8 bits to 100th slave, it is going to take 8 microseconds itself. Whichever, how much ever slaves it might be, there is point to point communication happening, and it is always taking 8 microseconds of time to make sure 8 bits of data is being transmitted from master to slave. Okay, now let's go with the daisy chain configuration. So here I am going with the same scenario, means let's say here as well, master is the one who's going to generate the clock, and to generate one clock pulse, again master is taking 1 microseconds. Okay, now let's say there are 8 bits of data to be transmitted. If 8 bits of data has to be transmitted to slave 1, how much duration is it taking? If master wants to transmit 8 bits of data to slave 1, so it is going to select slave 1 like this, and it wants to transmit the data to slave 1. Yes, it is going to take only 8 microseconds. So for generating every clock pulse, master is taking 1 microsecond. So to make sure the master is transmitting 8 bits to slave 1, it is going with 8 microseconds of duration. Now, what if master wants to transmit to slave 2? So it is going to select the slave 2 like this. And master wants to transmit 8 bits of data to slave 2 this time. May I know how much time it takes to make sure 8 bits are being reached to slave 2? Don't you think it is 16? So first 8 bits, because first of all there is no point to point communication happening. Master transmit 8 bits to slave 1 using 8 clock pulses. Again from slave 1 to slave 2 it has to come like this. From slave 1 to slave 2 it has to come. So again 8 bits of data needs to be transmitted and 8 more clock pulses. So a total of 16 microseconds is what this master takes to reach 8 bits of data to slave 2. And what about slave 3? Yes, it is going to go with 24 microseconds. So 8 microseconds to make sure data has reached slave 1. Then from slave 1 to slave 2 it is 8 microseconds. Again from slave 2 to slave 3 another 8 microseconds. A total of 24 microseconds is what it takes to reach the data from master to slave 3. So now I hope you got an idea. Whenever you want point to point communication to happen, and there is a time criteria given to you, you have to go with the normal configuration. And whenever you are okay with not having the point to point communication, and you're okay with any time constraint, and you still want the hardware configuration to be reduced, you have a constraint on hardware configuration, and you're okay with any given time, you have to go with the daisy chain configuration. Understood this example? Everybody? Okay, fine. Now, there is one more scenario. Okay. So, one scenario, as I said, is when the data transmission has to happen. Now, one other scenario, in fact, I'm going to go with two scenarios. So, what happens in this case is, let's say there is a single master who wants to communicate with 3 slaves. Okay. So, there is one master who wants to communicate with 3 slaves. So in that case, let's say one slave, first scenario is you have got 3 same slaves. Okay, so let's say I'm going with 3 temperature sensors. So assume you have got some gaming laptop, and first of all, to generally monitor the temperature of the motherboard, there will be one temperature sensor. So assume to monitor the overall temperature of the system, there's another temperature sensor. And basically for the graphics card, let's say it is making your system heat up. So to monitor that, let's say we have got another temperature sensor. So basically there are three slaves. So I'm least bothered with what these temperature sensors are doing. So just an example, there are three same slaves, let's say three temperature sensors. And another scenario is there are three slaves, three different slaves. Okay, so let's say one is RTC, the other one is external EEPROM. Okay, and let's say there is not actually external EEPROM, so just a EEPROM. Okay, and let's say there is some other sensor, for example some IR sensor, I'm not sure, some other sensor. Okay, let's say go with the temperature sensor only. So first thing, there is a master who wants to communicate with three slaves. First scenario is all the three slaves are same. Second scenario is three different slaves. Now, if there is three same slaves, which configuration are you going to use? Normal configuration or daisy chain configuration? May I know which configuration you might be going with? You can just tell me whether it is the normal configuration you're going with or the daisy chain configuration. Okay, so I agree with daisy chain in this case. The reason is most of the time. Okay, first of all, another question. If I'm going with three temperature sensors, tell me, are you going with the same manufacturer or three different manufacturers? If you want three temperature sensors, do you go with the same manufacturer or three different manufacturers? Different. You think you will go with different? First of all, I am going with the intention of just monitoring the temperature. Okay. I always see we people think smart at times. Always want my task to be taken easily. So if I'm going with three different manufacturers, don't you think I have to learn three different set of instructions? Do you do that? Do you think I can do that? Just I want to monitor the temperature. Why will I have an extra work taken? I will go with the same manufacturers. First thing is it is cost effective. If you take things on bulk, you will get it in a lesser price. It is cost effective. Second thing is only one instruction set is what I have to be learning. I don't have to learn three different instruction sets. So if I know the configuration of one temperature sensor quite enough, I can make sure to configure the other temperature sensors also. And remember, if the devices are same, they will have good compatibility between them. So connecting to same temperature sensors are easier compared to connecting to different temperature sensors. So remember, whenever you have got three same slaves, we are going with a daisy chain configuration. The only reason is the slaves with them will have a good compatibility. And second thing is, once I have got an instruction set learned, I don't have to be learning extra number of instructions. So that is the first reason why I will go with the daisy chain configuration. And when there are three different devices, so I'm definitely going with the normal configuration. The reason is anyways I have to learn three different instruction sets and I'm definitely not sure how compatible the three devices are with each other. So making sure to connect one slave with the other slave with another is quite risky at times. So if there are three different devices, I'm going to go with the normal configuration. So where I'm going with three different slave select lines and I am going to configure the three things separately instead of getting the things interconnected to each other. Okay, so it is easier to go with the daisy chain if you have got the same slaves, and it is easier to go with the normal configuration when you have got different slaves. Has that been clear? Okay. So now I want to take one simple example, one last example. So if there are three different slaves, it is literally easy. Okay, we are going with a normal configuration. You're going to select a particular slave, and whenever you want to write a data to the particular slave, you just can go with the slave select line, write the data directly to the particular slave, because there is point to point communication. Now, have to make sure a particular data is returned into a particular slave using daisy chain, because there is no point to point communication. If you can notice here, there is no point to point communication. If I have to write the data to slave 2, I have to first write it to slave 1, then it comes to the slave 2. There is no point to point communication. Now, how will I make sure a data is being written just to slave 2? I don't want to write to slave 1. I want to write it into just slave 2. For that, let me go with a simple example. Okay, just to make you understand how the data can be written, I'm going with a simple example. So here I'm going to take a speaker. Okay, so let's say you have got a speaker taken here, and speaker, if I said I'm going with the daisy chain configuration only if the slaves are same. So assume I have got a speaker and there are 3 DACs inside it. Okay, so it is digital to analog converter. So there are 3 DACs inside it. There's a speaker I have taken, and speaker is having 3 DACs inside it. Okay, let me give the name as, these are the 3 DACs. I'm giving the name as slave 1, this one as slave 2, and this one as slave 3. Okay, so I'm giving the 3 names. And as I said, uh, this I'm going to have the connection done using a daisy chain configuration. And remember, whatever signal is being passed here, the digital signal, this is DAC I have taken, the digital signal has been converted to an analog signal. Okay, so this is my microcontroller. Let's say this is my microcontroller, and I have got 3 slaves with me. This is slave 1, this is slave 2, and this is slave 3. And according to the daisy chain configuration, I'm following the same. So I'm not writing any clock pulse. Okay, so it is understood master is going to generate the clock pulse. And let's say master, this is been connected like this. Master is been connected to slave 1, and like this. And slave 1 has been connected to slave 2. So I'm going with the daisy chain as I said. So slave 1 has been connected to slave 2 like this. Okay. Please give me a moment in order to do this. And slave 2 is being connected to slave 3. So now the thing is, okay, I'll also make sure the slave 3 is being connected to master. So usually what happens is not all the slaves will have the compatibility of writing into the master. So it differs from the system to system, how the slave has been manufactured. So this time let me ignore. Assume I have no ways of writing from the slave back to the master. So I'm just ignoring it. So this is the master, which is our microcontroller, and sorry, this is the okay, this is our microcontroller. This is slave 1, this is slave 2, this is slave 3. Now, I'm just giving you a simple scenario. Okay, so assume basically they will have the shift registers, you already know, and because these are some electronic devices, they will have some garbage value for sure. So let's see, this master's shift register right now is having some data like 0x1f. I'm just taking. This slave is, this shift register of the slave is basically having some data 0x1c. Just an example, 0x1c. Let's say this is having another uh, data which has been present internally initially 0x maybe 1 1, and this I'm going with let's say 0x 2D. Okay, just an example. Okay, so this is my master, this is my slave. I will just give you a simple example. Assume you're watching a horror movie. Okay, so an assumption, what you are watching a horror movie, and there's a speaker which has got three DACs. Let's say one DAC is to control the sound of the wind. Okay, assume one DAC is to control the amplitude of the wind sound. Another DAC, let's say, is being used to monitor means vary the amplitude of the ghost entry. And let's say another DAC is being there. Assume it's raining, and maybe in the scene it's raining, and maybe there is another DAC who is monitoring the sound of the water droplet. Okay, just an example. Okay, so there is one DAC who is monitoring the wind. There is another DAC who is monitoring the sound of the ghost, and another DAC who is monitoring the sound of the water droplet. Now, if you have noticed, suddenly when a ghost entry happens in the movie, what happens with the amplitude? Suddenly, if there is a ghost entry you are seeing in the movie, what happens? Come on. What happens suddenly if there is a ghost entry? Don't you think the amplitude, the sound gets increased? Isn't it? Suddenly the sound gets increased. So which DAX sound should I be increasing? Out of the three available here, which DAX sound I want to increase? The second one. I want this to be made as high. So let's say the highest here is definitely it is 0xFF. I want the ghost DAC to be reached with 0xFF. The rest I want to keep it as it is. Now, so there is a scene happening, and when the ghost entry occurs, I want this ghost to have the DAC which is controlling the sound of the ghost entry needs to be raised high to the amplitude. So what happens? I want to write this DAC with 0xFF. Okay, how will I start writing? I will start writing from the microcontroller. So in this master, let's say, first of all, I don't have direct access to write into the slave. Okay, that is not possible. So I have to transmit. The master has to transmit to the slave first. So let's say I have got the built-in SPI block with me. I'm going to write the buffer register with 0xFF. Okay, just assume I'm going to write buffer register with 0xFF. That 0xFF gets returned into the shift register of the microcontroller, and data gets shifted to the slave one. So now what happens is, so there is 0xFF I wrote. So that 0xFF got returned into the buffer of the master. Then that came to the shift register of the master. So 0xFF gets shifted here. Okay, so here I get 0xFF. But what happens with this data which was here at 0x, the 0x1c, that comes here. So here comes 0x1c, and whatever was here 0x11 comes here. Correct? Do you people agree with what I say? So there is a shift register here. All of these have got the shift register. There is a shift register here. 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 So initially the shift register had some garbage value like 0x1f. This had 1c, this had 11, and this had 2d. The moment I route 0xFF to the buffer register of the microcontroller, that is the master, that data was returned into the shift register of the master, and that got shifted to the slave. So 0xFF came here. Whatever was here, got shifted here, which is 0x1c. Whatever was here, got shifted here, which is 0x11. Now, did we achieve what we require? Did we achieve what we require? No. So what I will do is, I will write 0xff for another time. So I write 0xff here. Now data will come to the shift register here. So 0xff gets shifted here. It comes here, 0xff. Then whatever 0xff was in the wind shift register, it comes here, which is 0xff. Again, whatever was here comes here, which is 0x1c. Now, did we achieve what we require? Did we achieve what we require? Yes or no? Yes, we achieved what we require. My intention was to make the DAC of the ghost be written with 0xff. I have achieved it. Do you people see anything happening here apart from this? Yes, don't you think we changed the value of DAC1 and DAC3 as well? Yes or no? See, I didn't want to change the amplitude of wind and water. It was 1C. I made it FF. It was 2D here. I made it 1C. So just to make changes into the ghost DAC, I made changes into the other two DACs as well. And is this preferable? Do you think this is preferable? Definitely not. So how are we going to achieve this is, usually we go with a array taken. Okay, so we generally go with an array. So after I go with an array, what I do is, so let's say initially with the same thing. So initially this master shift register is having 0x1f. This slave is having 0x1c. This is having, let's say, okay. So this is having 0x11. This is having 0x2d. Okay. So what I will do initially is, whenever I want to write it into a specific slave, so I make sure whatever value is being present in the shift register is being stored into an array. So I take an array because I have got 3 slaves. I take an array of 3 elements. So I write the value here. 0x1c is what the first slave has. 0x11 is what the second slave has. And 0x2d is what the third slave has. So 0x2d. Okay, and then what happens is, after this, whatever data I want to change, I want to change only the second DAX value. So this I will be changing with 0xff. Okay, so only this I will be changing with 0xff. I go to this array and I change the value of this array as 0xff. Okay, so now what I will do is, instead of writing this data, I write it from the end. So first I will go to the master and write 0x2d. Okay, I'll go to the master, write 0x2d. So whatever I write in the master comes to the slave 1. So 0x2d comes to this slave 1. Then whatever was in slave 1 comes to slave 2, which is 0x1c. Okay, whatever in slave 1 comes to slave 2 comes to slave 3, which is 0x11. Then I'm not done. I will next write 0xff. Okay, so whatever is in slave 1 comes to whatever is in the master comes to slave 1. So this ends up getting 0x ff. So this ends up getting 0x2d, and this ends up getting 0x1c. So I'm not done again. I write 0x1c this time. Okay, 0x1c. So whatever is in the master comes to the slave 1, which is 0x1c. So whatever is in the slave 1 comes to the slave 2, which is 0xff, and whatever is in the slave 2 comes to the slave 3, which is 0x2d. Now, do you see? In wind, I have got 0x1c. In ghost, I have got 0xff. In water, it has got 0x2d. Now, don't you think we achieved what is required? So, I made sure only the DAC 2, that is slave 2, is being written with 0xff, and the wind and the water means DAC 1 and DAC 2 I have retained same. See, it was 0x1c, now also it is 0x1c. It was 0x2d, now also it is 0x2d itself. I only made sure to change the DAC 2's value. So this is how you make sure a particular data is being written into the particular slave when it is a daisy chain configuration. Understood this? But before slave 1 and slave 3, before has been okay. Things happens in fraction of seconds. Happen in fraction of seconds. So just for a fraction of second it has been changing. You will not even get to know that. Okay, as you can see in the pulse width modulation, if you can see, what we discussed was, if you increase the frequency, the change happens in a very faster manner that we human people cannot even identify there was a change happened. So things happens in a very swift manner. But anyways, I'm not constantly changing it. Everything comes with advantage and disadvantage. So this has got a disadvantage also. As Vivek says, we'll have to be performing more number of right options, but we don't have an other way of doing it. So if you have got hardware constraint, when you have got less number of hardware wires to be used, and you cannot go with the normal configuration, and the only option left with is the daisy chain, it comes with its own disadvantage. So nothing has been perfect. Everything has got its own advantage and disadvantage. In this scenario, how to make sure to write a particular data to a particular slave is like this. Got it? Guys, is this been clear? And actually, this is it about the SPI protocol. So we don't have SPI block in our system. Sorry, in our microcontroller, we don't have the compatibility for the SPI protocol. So if we still want to achieve the SPI protocol, maybe we'll have to generate the clock pulse, then do the shifting of the data from one register to the other. So we have to literally do it by ourselves. And you already know how to generate the clock pulse, how to make the shift operation happen, which is why we don't have a code for the SPI protocol. And this is about the SPI protocol in detail. The next we have got is I2C protocol, which is inter-integrated circuits protocol, which we are going to discuss in tomorrow's class. Are you people clear with the SPI protocol? Okay, fine. So please wait, let me have the attendance marked. I think ma'am so far has been using this scanner itself, right? Are you people familiar with marking your attendance with the scanner? Okay. All right, so let me have the scanner shown. Please be ready to mark your attendance, and whoever is done marking the attendance can leave the session. You have class tomorrow and we are going to discuss I2C protocol, which is really important. So we have got the code for that protocol as well. Code is important to be understood. So please make sure you are attending tomorrow's class, and please be on time, because if you're joining somewhere in between, it will be difficult for you people to get back to it. So whoever is done marking the attendance, you can leave the session. And for those who are not able to mark it, I'm going to send the link using chat box. Please mark your attendance. And whoever is done marking the attendance, you can leave the session. Is a situation possible where two slaves are trying to communicate with master at the same time? So first of all, there is only one data, there is only one clock line available, and there is only one time transmission happening and reception is happening. So two slaves communicating at the same time is not possible because there is a slave select line. First of all, in the normal configuration, master is going to select the slave using a particular slave select line. So there are no ways he is going to select different slaves. Two slaves at the same time. So that is not possible. So it selects the slave using active high or active low signal only. And when it comes to the daisy chain as well, you can make sure there is only one slave being selected at a time while communicating. Okay. All right, guys, those who are done with the attendance can leave the session. Thanks for attending the session, and we'll meet tomorrow. Thank you all. And please be joining on time. Code is being okay. So let me reload. I guess you can see it now. So for every 30 seconds, it keeps changing. You have to update the new code. So I'll wait until everybody quits the session and then I'll close the session. So please make sure you're marking the attendance and then leaving the session.